Hi there, this is Mr. Sand, and I'm going to walk through the relationship between position, velocity, and acceleration in graph form. And I think the easiest way to do that is just to start off by looking at a graph like this. Okay, so on this graph right here, this is a graph of position versus time. So it shows something's position, some object's position. We'll just call it a ball for this case right here. This ball starts off at the origin point at 0, 0 time right there, time, 0 time, and 0 position. And then after 10 seconds, it has moved 60 meters away. Then the ball stays at 60 meters for, it looks like, if these are correct, you got to look at these, the scale right here. This looks like it's a 5, 10, 15, 20. Yep, so it stays for 5 seconds at 60 meters. Then this ball looks like it goes back to the origin and gets back to the origin at 30 seconds. And at which point it then moves away from the origin again, but now it's going in the opposite direction. This graph right here shows you not only how far this object's moved away, but where it's moved away to. So this now goes in the opposite direction past the origin, and it goes negative 40 meters away from the origin at 40 seconds, and then it comes back to the origin again at 55 seconds. So here is its position. It's going all over the place. You might be thinking, okay, great, that's fantastic, Mr. Zan, I understand that, but how does this relate to the velocity graph? And how does this relate to the acceleration graph? Well, I'm here to answer that. So let's take a look first at the velocity graph. I'm going to try to make this right above this graph down below here, so it's a little bit more clear. I'm going to get a black color for the, I hope we've got black. Yep, there it is. Okay, so I'm going to try to draw this as close as I can to that graph down below. So this is going to be position, this is going to be velocity and time. Now time is going to stay the same. Okay, time is going to stay the same. So I'm going to try to make this as close as I can to the same. So that's going to be 10. This is going to be at 20. This is going to be at 30. This is going to be 40. And 50 right about there. Okay. Now for velocity, I don't need to pay attention to these values right here for my velocity graph, because the velocity graph is going to have a different value system over here, or value range over here. And it's always going to be in meters per second for my velocity. Okay, so I know that there's something crucial that happens. Well, let me just step back right here. I know that at certain points the position changes. So I know that, well, throughout here the position is changing, and then here it's staying constant. Here the position is changing. But there are certain points which I know seem like they're important, because it seems like the rate at which this object's moving changes. So I know 10 seems to be like a major point. 15 seems to be a major point as well. That's right here. And 40 seems like it's a major point because it's changing its rate right here. And, well, it goes all the way to 55. So let me just, oops. Okay, 55 is probably like around there. Yeah, something like that. Anyway. Okay, so what is a velocity? Velocity is meters per second. So if this is just meters, well, meters per second is this slope right here. It's the change, it's the rise over run. It's meters per second. So what is the slope of this line right here? Okay, that is what the velocity is. It's the slope of the position versus time. Okay, so it's the change in the position versus time graph. So from 0 to 10 seconds, what is the slope of this line right here? I'm saying from 0 to 10 because I know it's the same slope throughout that period. So from 0 to 10, what's the slope? Well, it's gone up how much? It's gone up 60, and it's gone over 10 seconds. So rise is 60 over 10. Well, that's 6 meters per second. Okay, it's gone up 60 meters. It's gone over 10 seconds. Well, that's the same as 6 meters per second. So I know over here, I'll say that's 5 and that's 10. Okay, so that means from that 0 time point to the 10 seconds, well, that means that this object stays the same, 6 meters per second from that time to that time. So that's our velocity. Okay, now from 10 seconds to 15 seconds, what's the slope here? The slope's 0. So I'll put 0 right here. Okay, I'm not filling this in with any lines or anything like that right now. 0. It's 0. Okay, from 15 seconds down to 40 seconds, this line is the same slope. So what's the slope here? Well, I'm just going to go from here down to right about there. So this is, it goes down to 60, so it goes from negative 60. And how many seconds between here and here? Well, that's 15, 20, 25. So 60 divided by 25. What is 60 divided by 25? I gotta use a calculator for that. It's almost 2, but it's not quite. 60 divided by 25. Oh, it's 2.4. So it's negative 2.4 meters per second. So if I make my graph correctly, this distance right here is about the same as this distance right here. This is negative 5. So this is going to be negative 2.4. So it's going to be almost right in the middle of this mark right here, which is 0, and here. So it's going to be right about there. So let's see, from this point, 15, all the way to 40 seconds, it's going to be the same. Namely, it's going to be negative 2.4. Okay? Now from 40 seconds on to 55 seconds, it changes here. It goes up 40, that's its rise, and the slope is always the same here. It goes up 40, and how many does it go over? So it goes over 5, 10, 15. So it goes up 40 and over 15. So 40 divided by 15 is 2.667. So 2.67 meters per second. So from 40 to 55, that's all the information we have in this graph right here. We know that the velocity is about, it's right about there. And it stays the same. How do I know it stays the same? Because this slope does not change. This slope right here is at negative 2.4. That's its rise and run. Right here, it's 0. That's we have 0. And right here, it's up 6. So it's a 6 meters per second. So that's its velocity. Now, if I want to, I can do this. I can connect these with vertical lines. That makes you feel happy. Makes you sleep better at night. That's fine. All right? But really, our velocity, in this graph, what it's saying is our velocity goes, oh, it's 6 meters per second, and then boom, it goes down to 0 right away, instantly. That's what this graph is showing you right here. Then it goes negative, like down there. So it goes negative for a long time. It stays at that slope for a long time. So this is our velocity versus time graph. And over here, it goes positive again. So our slope right here is a positive slope, and this is going to be a positive velocity right here. So this graph is the change of this graph. Okay, so that's the change of this graph right here. So it's just showing you what the changes are. So this is the slope right here, that's a slope right there, that's a slope right there, and that's a slope right there. It's just reporting you the slope. The slope of the position versus time graph is this right here. That's a velocity graph. Velocity versus time graph, I should say. Okay, now it's kind of hard to draw, to be honest. It's kind of hard to draw an acceleration versus time graph from this velocity versus time graph right here. Now, why do you think that is? It's because the slope right here is 0, and then here it looks like it's infinity. It's like perfectly straight. And here it's 0, and here it looks like it's just perfectly straight up and down, so it's like infinity. And then here it's 0, and here it's perfectly straight up and down, and here it's 0. So it would look like, and for an acceleration graph, it would look something like if we were going to draw this acceleration graph from here, it would look like 0, 0, 0, and then like a spike to, well, here would go downwards, like to a negative infinity, I guess. And then it would go 0, 0, 0, and then another spike, and then it would go 0, 0, 0, 0, 0, 0, 0, and then a positive spike, and then it would go 0, 0, 0, 0, 0. So this is a very odd graph to show you based on this graph right here. So normally what happens is we give you like a velocity versus time graph, and we say from here, draw an acceleration versus time graph, in which you do exactly the same procedure I just did with the position and the velocity graph. Namely, you would just find the slope of a velocity versus time graph, and you would report that as your acceleration versus time graph. Okay, so let me just put this in regular, well, I'll just put this in a couple ways. So first of all, the change of the position versus time graph is a velocity versus time graph. And now, the change of a velocity versus time graph is just the acceleration versus time graph. In other words, the acceleration versus time graph just shows you the slope of the velocity versus time graph. And the velocity versus time graph shows you the slope of a position versus time graph. Okay? I've gone through how to graph a velocity versus time graph based on a position versus time graph. Now, what I could do is I could say, all right, I'll just give you a different problem here, and I'll change this word right here into velocity, and this will be like 80 meters per second, 60 meters per second, 40 meters per second, 20 meters per second, and so forth. And I'd say, okay, this is a velocity versus time graph. Now tell me what an acceleration versus time graph. And it would look just like this graph right here, except it would then say, instead of v, it would say accelerate a, it would say meters per second squared. So this is the slope of this graph. It's graphing the slope of this graph. So if I would say that this is a velocity versus time graph, this would be then the acceleration versus time graph. I hope that makes sense. Okay. That's how you graph the slope of another graph. I think that's the clearest way I can describe it. Sometimes we start off with curves. Let's say that we have, I'm going to give you a brand new